And our first speaker will be Ludovic Planté, who will tell us about classical gravity from loop amplitudes. So please go ahead, Ludovic.
Okay, thank you. So I would like first to thank the organizers for the invitation. I will speak on classical gravity from loop amplitudes. So it is a presentation based on the work we just published last month and last week on the computation of 3 PM amplitude from techniques I will explain in this presentation. But it was done in collaboration with Emil Björn-Borg, Paul Damgaard, and Pierre Vanov. So what I want to, So what I would first do is give some motivation and definition on the computation we have been doing, and then give some one loop example on how the technique we are using is working at one loop. After that, I will explain the two loop computation we have been doing in both supergravity and Einstein gravity theory. And then I will do a short focus on the computation of the integrals, which is a key in this kind of computation. And after that, I will conclude. So first, the main objective of this talk is to present the techniques we have been developing in the two papers I was just citing, which in fact, the main principle is to assemble integrants in gravity, so that you see appearing some delta function that we call velocity cuts in our last paper, that reduce the dimensionality of the integrals that you have to compute. And so it simplifies a bit the integrals you have to compute. And it also, so we have been able with that to clearly separate the iteration of subloop integrals in the iconal matching procedure versus the integrals that you really want to compute in the 3 PM observables. Then I want also to point what is exactly the difference between the potential and the soft region computations, and also identify how to make contact between the amplitude and the world line formalism, and how the iconal matching procedure works at the integral level. So we are computing a two-body interaction, so 4-point amplitude with two particle with particle of mass m1 and m2 that are interacting in gravity, both supergravity and Einstein gravity. So you can define a Mandelstam variable S, which is the square of the energy in the center of mass frame, and T, which is the square of the momentum transfer. Then U is linked to S and T as it is known, and the sigma is linked to it's just P1, P2 over M1 and M2. So at the end, the amplitude is just a function of the 4 parameters, Q, sigma, and the masses. So you could try to do a computation of the amplitude in these all 4 parameters, but it is simpler to do a soft expansion in Q, which is also a lower expression in H bar, so that you can identify the classical, you can do a classification of the different contributions depending on the classicality of each contribution. Then the computation of the amplitude is done in Q space, so in momentum space, and it is important for the matching procedure to go in B space. So this is given by this Fourier transform. I think you can see also Carlo Heisenberg talk for this. I think we are using the same method. So then after you go to B space, you can do the iconal match procedure, which link in fact the amplitude here to the iconal quantity. So the classical little delta, which is a phase which is classical, so which has the power h bar power 0, so it's purely classical. And then the big delta, which are some quantum pieces that appear also in the amplitude. So when you have this expression, you can then make a link between the amplitude and the different quantities in the iconal formula, like big delta and little delta. So at tree level, you have a direct link between the tree amplitude in B space that assemble like this. So the -1, the index here is just the order of h bar. So the classical amplitude is so it's 1 over h bar, so it's -1. So the tree amplitude is directly linked to delta 0 like this with a factor of 2 over h bar. Then the one loop amplitude has first a super classical component, which is just the square of the tree amplitude. and then a classical component, which is directly linked to delta 1. And then you can also compute some quantum correction to the one loop amplitude, which is 2 peak delta 1. So at 2 loop, it's the same. It's a bit more complicated, but you have the super classical term, which is power -3 in h bar, and which is the cube of the tree. And then you have the super classical, which is the product of the tree level amplitude and the one loop classical contribution to the amplitude. And then the classical, I think this is the place where there is the first non-trivial check for classical computation with the diagonal, because for the classical correction to the two loop amplitude, you have the delta 2 term, which you want to compute a classical observable like the angle, but you have also a term which is the tree amplitudes times the quantum correction to the one loop amplitude that you have to cancel, in fact, in the matching procedure. So first, I will give some one loop example. I will start by the box integral. So the idea is to look at the amplitude in n equal 8 or in gravity, and see that in up to, so at classical order, and I think it's n equal 8, it's exact, but as in gravity, it's only valid up to classical order. So you have a remaining terms here, but for classical quantity, you can see that you have the same coefficient in front of the S box, which is this one, so the box in the S channel, and the cross box, so the box in the U channel. So you don't need to compute individual integrals, in fact, to compute classical terms. You only need to compute sum. And to do the sum, so as I explained in the introduction, we do a soft expansion. So we rescale the internal momenta like this, and Q like this, with UQ, which is a unit vector, so UQ square equals -1. And then you scale also the Q like with H bar, so that you can do also the Laurent expansion in H bar. So when you sum the two boxes, you arrive to this expression, where you see that thanks to the rescaling, there is a coefficient Q. So it's in G equal 4, it's 1 over Q square, and then 1 over H bar square. So here you see, so you have 4 terms, but it's because here you have two. So P1 prime, P2 is a U box, P1 prime, P2 prime is the S box, and the same for P1, P2, and P1, P2 prime. So that's why there is an extra factor 1/2 that you have to put here. But at the end, using this expression, you can then also expand the external momenta, like P with a bar coordinate, like a P1 equal P1 bar plus H bar Q over 2 UQ, and you do the same with all 4 coordinates. And you do the soft expansion also on this massive propagators. So you see directly that for the super classical term, P1 prime will be equal to P1 bar, and P1 will be also equal to P1 bar. So here you have automatically a delta function that will appear, and here it's the same thing for this quantity. So you have first a super classical term, which is just an integral with 2 delta functions. So after you take the delta function, you will only get a D-2 bubble, so which is very easy to compute. And you check that it is of order 1 over Q square and of order 1 over H bar square. So it is a super classical term. And then, sorry. So then you have to expand in Q, as I said. So at first order, you can expand this term or this one. So if you expand this term, you will still have a delta function here. And if you expand this term, you will still have a delta function here. So at the end, you have only one delta function on the classical term, which is the classical term, so 1 over H bar. And in Q, it's a 1 over Q. So then you have to do the same thing with the triangle, which is more simple, I think. So which give only one delta function, and you can classify your amplitudes in a super classical term, which is 1 over H bar square, with 2 delta function, and a classical term, which is just a term with one and integrals with 1 delta function. And in fact, there is a 1-to-1 match between this classification in delta function at 1 loop and the diagonal matching procedure. So you have these 2 delta functions which correspond to exactly to the 3 squared that will be cancelled in the diagonal matching, and then the classical that you want for delta 1 is only the integrals with the contribution with the integrals with one delta function. So you can interpret that with some velocity cuts. So you can say that this delta function acts like cuts. So for this term, you cut with two delta functions. So in B space, and I should say it's important that it is in B space because the matching is only valid in B space. For the super classical term, you cut the box with two lines. So you separate the two tree, and in fact, it gives you the tree square. And for the classical term, you just take one delta function, and it gives you just directly the M1 classical or the 2 delta 1. So at one loop, it works perfectly. So the question we wanted to ask in our two papers is does it work at two loop? In fact, the answer is yes. So first, at two loop, you have to classify your two loop topologies. So you do the soft expansion in Q, as I said, and you do the Laurent expansion in H bar. And the first thing you have to do is to classify your integrals in terms of which one are quantum, which one are classical, which one are super classical. So when you count the H bar and the Q, you arrive to the conclusion that these kind of integrals are purely quantum. And that in fact, the classical integrals are just the integrals which have two massive propagators. So the H diagram, the double triangle, this you can call a mushroom, and then or self-energy, and then you have the box bubble. So these integrals are of order 1 over H bar and will be classical. But they will not contribute, so all will not contribute to the delta 2, in fact, but we'll see that later. And then you have the integrals with three massive propagators, which are the box triangle and some self-energy diagrams also here. So these integrals will contribute at order 1 over H bar square. So like a super classical term. And you will have also a classical correction of this integral because you have to expand the propagator, the massive propagator. So you have also a classical contribution from these diagrams. And then you have also the double box and the self-energy ones that have 4 massive propagators and that are super classical with also correction. So super classical correction and classical correction. So at the end, you can decompose the amplitude in several topologies. So there are only at two loop 6 independent topologies. So you have the double box, the box triangles on the two sides. So I didn't sketch all the box triangle, but so you have the box triangle, then the double triangle, the H, the box bubble, and the self-energy diagrams. So in inequalate, so we started to work on inequalate because it's a more simpler, so it's a simpler case. The amplitude is just this in inequalate, where I neglected some terms which are subleading in Q. So we are just looking to soft expansion in Q up to classical order. So the main idea is that you don't have to compute each individual integral because so here what I call GS, it's the sum of all integrals in the S channel, the double box integrals. And the GU is the sum of all double boxes in the U channel. And the GT is the sum of all the H diagram in the H diagram. So it's just the H plus the H when you exchange P1 and P1 point, for example. So instead of computing not a lot, but perhaps 6 or 7 integrals, you just have to compute 3, which is the sum of all double boxes, which is GS plus GU. Then the sum of U double boxes and the sum of H diagram. So and GT and GU just have to compute them at first order in Q, because you have already a Q square in the numerator here and a Q4 here. And GS plus GU is the only one that you have really to expand, in third order in Q. So the most complicated is this one, but these two are not so complicated. So I will start by GT. So GT is the H diagram. So the massive propagator have the same structure than in what you have seen in the one loop box. You just have to add the GT in the S channel and the GT in the U channel, and then you arrive to that. But at two loop, the the graviton propagators are not the same, obviously, but so it's more complicated, but you can still, at leading order in Q, take the delta function here and the delta function here, and you arrive to this result. So, and this is really like what is done in the world-like formalism when you cut this massive lines, and you arrive to some graph when you replace the massive. So you have some massive source here, and you just have to compute the integral with the two delta function. So I will not explain here how we computed the integral. I will do this later in the presentation. But at the end, we have the final result, this final result, where you see that for the H diagram, you just have the term with pi. So pi r cosh is the potential contribution that you find in the literature, and then you have some radiation reaction term with a factor of -1/4 sigma square -1, where the -1 power epsilon is the factor that is responsible for the relation between the imaginary and the real part of radiation reaction. But I will comment that later. So the GT is this. So now I will not explain GU because it's the same ID, but I can explain GS plus DU. I think it's the most interesting. So GS plus DU, as I said, it's just the sum of all the double boxes at two loop. So this is this quantity where I already put the P1 and P2 in the bar coordinate. So with the plus Q UQ Li over 2. So we have to expand this, in fact, at third order in Q. But first, if you look at the leading order in Q, so you can take Q equals 0 in each propagator, you will find that it is really like the double triangle. So it's a double triangle square on each side for each massive. So it will give, in fact, each one delta function by massive propagator. So the super classical term is just 4 delta function, and it has a coefficient 1/h bar cube, and it's 1/q square on the dependence on q. So it's just you can say it's just 4 velocity cuts on each massive propagator. Then you have to expand one time in q. So when you do this, you expand one of the massive propagator. So, and you get 3 delta function, in fact, on the other one, which have still a coefficient 1 on the denominator. So you have 2 possibilities. You get this delta function where you take 2 delta function. Yes, so one delta function on the P2 side and 2 on the P1 side, and you have the opposite way. And this is a term of order 1/h bar square. So it is a super classical term, and it's 1/q. Then for the classical term, it's a bit more complicated. So you have to expand this to third order so 2 times in q to get a q square. So to get a q power 0 or q power -4 epsilon and a 1/h bar. And then you have several possibilities. And when you do this, you see how the delta function emerge, and it's emerging with the 4 contributions. So first, you have the contribution when you take 2 velocity cuts regarding the same internal momentum. And then you have the other possibility is that there is delta function with a different internal momenta in this delta function. So I put this in orange and this in red for later convenience, but this is really two different kinds of integrals, and it will not contribute in the same way in the amplitude and in the iconal matching. So these 3 are really almost the same. It's just that here you take the delta function on the same particle on the left side of the graph, and here it's just you mix P1 and P2, and here it's P2 on the both sides. So then you have to sum all the contribution. So as you remember, there were 3 contributions, but the GS plus GU is the only one contributing to the super classical and the super classical. So at the end, what we find is that it is exactly the same thing that at one loop that happens. It's the fact that if you take the super classical term, so the h bar 1/h bar power 3, you have, as I just shown, you have 4 delta functions, and it corresponds to a cut of the massive lines here. And you get exactly the cube of the 3 amplitude in B space. Again, it's important to be in B space. So for the superclassical term, it works perfectly. Then for the superclassical term, or for the 1 over h bar square, the same thing happens, and you get that it is exactly equal to a product of the 3 amplitude and the 1 loop classical part. And the interpretation in terms of graph and cut is the following. So you cut 3 massive propagators, so you have 2 possibilities, this one and this one. So, and it's factorized, so the tree is cut, and then so you have a 3 times a 1 loop with one of the side of the 1 loop box that is cut. And we have seen that at 1 loop that it means that it is the classical contribution. So this is very coherent with and logic if you think at the 1 loop case. And then, as I said, at classical order, at 1 over h bar, you have 2 kinds of contributions. So the first kind was the one with velocity cuts on the same internal momenta. So here you will have this kind of cut. And you see that here also the 3 amplitudes separate. So it separates, and then it is the product of the 3 times the 1 loop without any velocity cuts. So in fact, it is the quantum contribution from the 1 loop box. And we checked in the first paper that the delta 1 here is exactly, in fact, the quantum contribution in an equalate at 1 loop from the box. And at the end, the only contribution that contributes to delta 2 is the one with the when you cut on different internal momenta, and you cut this way. So here you have you have the contribution of GT, which is here, and so GS plus GU that we have just seen, and GU also contributes here. But you have a full classification of the diagonal matching and a 1-to-1 correspondence with the velocity cuts in an equalate. So at the end, when you have delta 2, you can easily go to the deflection angle. I will not give details of that here, but I think you can find it for example, in Carlo Heisenberg's talk or in the papers. I think it's known. So you have 3 contributions. You have the Schwarzschild contribution, the conservative Arc-Koch, which comes from the H bar, so the H diagram, and then you have a contribution which is a radiation reaction, which we found that we can put in a very compact way in a sigma derivative with 2 sigma square and the 2 sigma square here. And I will come back to that later. But this is a complete match with the paper of Di Vecchia, Heisenberg, Russo, and Veneziano, where they computed this term exactly also, but with another technique. So the question you could ask is, does it work in gravity? Because in an equalate, you have only scalar numerator, and you have a less number of integrals and diagrams. So it's a bit easy to do and to see how the integrals, you can add them to give delta function, etc. But yeah, the answer is yes, you can do it in gravity. And so we just published the paper that showed how we did it in gravity. So the main piece to consider is just the 3 graviton cut. I will not detail here the way to do the cut, but I think it was detailed in Radu Roiban talk last week. So I think I will not detail it here. But when you do the cut, you just have after that to decompose your cut in the different topologies that I showed earlier. So you have the double box topology, the box triangle, then the double triangle, the H diagram, and the box bubble. So first, I will redo the double box contribution computation. So the double box topology is very similar to what we get in n equalate. So it's just here the sum of GS and GU. So it's the sum of all double boxes. The only difference is that you replace 2 sigma square in n equalate by 2 sigma square minus 1. Then you have the GU contribution that we saw also in an equalate. And then you have a new contribution, which is a GNP, which is in fact the sum of non-planar integrals. And that can be, so you just need it to leading order in Q, because you have already a Q square in front of GNP. So you can very easily put it in a delta function form like this, and then compute the integrals with the basis I will show later. So at the end, we got a result for the double box, summing all the contribution from the three integrals GS plus GU, and GNP. So the result is the following. So it's the same thing that in inequalate, but a bit more complicated because we are in gravity. But the super classical term, which is the 1 over h bar cube, is still an integral with 4 velocity cuts, and it's exactly the 3 cube. Then the super classical term is the same that in inequalate also. You have to take 3 velocity cuts, and it gives the product of the 3 times the 1 loop contribution from the box. And then the classical term is a bit more complicated. So it's you have still the contribution, which is 2 velocity cuts, but with the same internal momentum here. So it gives just the iteration of the 3 amplitude times the quantum correction coming from the 1 loop box at 1 loop. And we check that it is exactly, I mean, we did again the 1 loop computation in the last paper. So we check that there is a 1-to-1 match between these two quantities. And then you have the contribution with 2 velocity cuts with different momenta here. And in fact, it can also be put in a very compact way using a derivative in sigma. And this is in fact the same result that in inequalate, except that you just replace the 2 sigma square by 2 sigma square minus 1, which is linked to the dilaton difference between the two theories. So then you just have the orange component which will be cancelled in the diagonal matching procedure, and you have the delta 2 contribution from the double box. So in gravity, you have also to add the other topologies correction or contribution. So as I said in the slide where I showed all the topologies, the box triangle so it will only contribute to the super classical term. So no super classical because it was in the double box loop. So the box triangle super classical contribution is just the insertion of 3 delta function, and it's the exact product of the 3 and the 1 loop triangle. Then as for the double box, for the box triangle, you have some ways to take 2 delta functions. So you have still this contribution, which is 2 velocity cuts with the same momentum here and here, and it will give exactly the quantum contribution. So the product of the 3 times the quantum contribution from the 1 loop triangle. So this is a very non-trivial check, I think. And then you have a contribution which is 2 velocity cuts with different momenta here and here. And it gives this contribution that will contribute in delta 2. So, and the last example is the box bubble. I think this example is useful to understand how the integrals behave. So the box bubble is only orange because you can only take. So if you want to take 2 velocity cuts, you have to take them on the same internal momentum here. So it will only contribute to the iteration of 3 times 1 loop. And in fact, we checked that it is an exact match. So it's non-trivial because the coefficient here of the quantum coefficient that gives the bubble at 1 loop is something like 1 plus 522 sigma square. So it's very non-trivial. And we check that there is an exact 1-to-1 match between this and the product of the 3 times the 1 loop quantum contribution from the bubble. So graphically, it's this. So you cut your massive propagator with the 2 delta function, and then separate this integral in a 3 times bubble. So at the end, so we have a match at the topology level. So the match works also on the amplitude level. So you have to sum all the contribution for all topologies and show that you have the diagonal technique works perfectly, and you can get delta 2. So for the super classical term, you just have the contribution for the double box. Then for the super classical contribution, you have the contribution from the double box and the contributions from the box triangle. And it is exactly the 3 times. So we saw that the double box gives the box at one loop, and the box triangle gives a triangle, and this one also this one. So when you sum, you just get the 3 of the product of the 3 times the classical correction to the one loop amplitude. And it is the same thing for the classical 2 loop amplitudes in this space. So you have to add all the contributions. So the contribution in red, it's the topologies with 4, which contributes only to delta 2. So especially the one with the 2 massive propagators. So the H diagram and the double triangle. And we had also, so we did the 3 particle cut, and then we computed also the self-energy diagrams. So you have also to add the self-energy. And then you have, at classical order, you have also the iteration implied by the double box and the box triangle that I showed earlier in the talk. So the double box giving the delta 1, the quantum contribution at one loop of the box, and same for the box triangle with the triangle. And then, as I just said, the same, the box bubble giving the 3 times the bubble contribution. So summing this, you get exactly the delta 1, so the one loop quantum correction that we were derived, in fact, in the last paper we published. So with this you can identify delta 2, and the final result is the following. So the 2 first line match with the pair and tal, the computation that was done 2 years ago, I think now. And then the second one match with the result of Damour and independently derived by Di Vecchia, Eisenberg, Rousseau, and Veneziano, with this factor -1. So we wanted to keep this factor -1/4 sigma square -1 for epsilon, for a reason I will explain later. But so you have a behavior here of sigma square -1, which is important, but you have also the -1 for epsilon that showed the relation. You see that here it's divergent. So it's imaginary and divergent, but the fact that you have a -1 for epsilon, it implies that you have a link between the relation between the divergent imaginary part and the real part of this radiation reaction term. And in fact, the -11/3 is just the contribution from the self-energy, and the derivative is just the contribution very similar to n equal 8, where you just replace 2 sigma square by 2 sigma square -1. So then, for the moment, I didn't explain how I computed the integrals, but so now I would like to show perhaps not exactly how we computed the integrals, but what are the main issues when you compute this kind of integrals. So I will just focus on the integrals that are relevant, meaning that it is the basis that contributes to delta 2, so not to the matching terms, because so I showed that it is the integrals that have two velocity cuts with different momenta here and here. So you have to consider this kind of integrals. So you can reduce the dimensionality of these integrals, in fact. But as P1 and P2 are not parallel, you don't have just bubbles. You have some generalized propagator here that will be responsible for radiation reaction, in fact. So you can consider this integral or this equivalently, depending on what you want to do. But then the technique, I think it was already explained in Mao and Carlos' talk. You then determine a set of master integrals. So we had 9 master integrals. And these 9 master integrals are sufficient for all contribution in delta 2. You don't need the extra integrals. And then you have a system of differential equation, which is written like this. and that you can solve. But now I want to show how the radiation reaction appears in this basis, and what are the difference between the potential computation and the full soft region. So the first example to consider, I think, because it's a very neat example, and I think it's the easiest integral to consider if you want to see the radiation reaction. So consider this mushroom integral. So you can consider it like this with two velocity cuts, so two delta function, or put it in d-1 form, like a bubble with a generalized propagator, like a tadpole, a massive tadpole. So the value of the integral is this. So you can ask, okay, how can I compute this integral? In fact, so you can first try a sigma -1, so a velocity expansion of this integral, and it will give you this infinite sum. And then if you try to do the L2 integration, here you just have a massless tadpole integration at all orders. So at all orders, it will be 0, and you will find that I5 is 0. And if you do a direct computation taking the other form of the integral, you can do the L2 integration with, for example, you have some formula, for example, in Smirnov appendix of his book, but you can do the L2 integration and then the L1, and you will arrive directly to this formula with the factor, the radiation reaction factor, if I can call it this way, with the power epsilon. So what is the problem in these two difference? It's just the fact that 24 is only valid when this term is small compared to this one. Especially if this one is on shell, you will have problems with this expansion. And it is exactly the potential region. So the potential region is the region where you expand this generalized propagator in sigma -1. But another way to see the difference between the two computations is to consider the differential equation for I5. So the differential equation for I5 is very simple. So the first way you can derive I5 is just, okay, you can expand I5 in epsilon. So you expand like this with each function I5n being a function of sigma. And then you know that I5 at 0, it's 0. I5 of sigma equal 1 is 0. So you can try to use the sigma equal 1 boundary condition to solve this integral with this expansion. But then if you consider, for example, I5 big M, it will be a constant because so its derivative will be 0. And then with the boundary condition at sigma equal 1 being 0, you will find that it is 0, and you will find that for all terms in the expansion. So at the end, you will find that I5 equals 0. But on the other side, if you do a direct computation of the solution of this equation, that can be done because it's an easy differential equation to solve. You find that I5 is just a constant C5 times sigma square -1 power minus epsilon. And the C5 is a constant of integration, but it cannot be determined by the sigma equal 1 limit, because I5 of sigma equal 1 is always equal to 0, whatever the value of C5 is. So the problem in this computation is the fact that when the sigma -1 expansion and the epsilon expansion do not commute, because if you consider this expression and you take the sigma equal 1 limit, you get 0 for all and then it's valid for all epsilon. But on the opposite, if you do the epsilon equals 0 limit on this expression, you get C5, and you will get C5 for all value of sigma. I have to say here also that in the computation, we had to impose that epsilon is negative to have a finite result for the integrals. And it is linked to the fact that these phenomena are due to infrared divergences. So I just gave the example for I5, but in fact, if you solve the system of differential equation, you will get also the same kind of result for all master integrals. So at the end, all master integrals can be written like this, with IN being equal to INP, which is the potential part of the integral, and so the radiation reaction factor times and R, which is the radiation function. And then if you try to solve the differential equation using a sigma equal 1 constant of integration, you will get only I and P, because limit of IN when sigma equal 1 is just equal to limit of I and P, and you will not see these terms if you just try to brutally do the sigma equal 1 boundary condition. To compute I and R, so we did the sigma equal 1 boundary condition to compute all these terms. And then for I and R, in fact, there was only one constant of integration. So the fact that we had I5 with a direct computation, it was sufficient to determine on all the value of I and R terms. So at the end, we were able to compute all the master integrals, both the potential terms, which are the terms of the sigma -1 expansion, and the radiation reaction terms. Okay. So at the end, what we have showed also is that there is an exact correspondence between the basis we have used with two velocity cuts here and here in one, each being applied to one massive propagator, and the basis being used in the worldline approach, and especially in the paper by Kaylin, Liu, and Porto. So it implies that everything I have said in the part where I explained the integral computation, it should be valid also in the worldline formalism. So it implies also that the radiation reaction should be present in the worldline formalism as it is in the amplitude computation, and the same way, because we are just considering the same integrals. And then I think the correspondence tends also to prove that we have found the minimal basis to compute the classical observables at 2 loop and delta 2, because we successfully put aside all the term that matches the 3 and 1 loop in the iconal matching procedure. So then you just have the only basis contributing to delta 2 is just the one with 2 velocity cuts of this form. So just to conclude, I think I just want to summarize what the method has for advantages. So with the method I described in this talk, we were able to compute classical terms of the two-body amplitude in n equal 8 and in ancient gravity at 3 p.m. So we did that by identifying in the integrand the contribution that sum, so that you can extract a delta function that we call the velocity cut in our papers. And depending on the number of velocity cuts and the kind of velocity cuts you are taking, you can identify the terms that will be cancelled in the iconal matching procedure, and the terms that are really the term contributing to delta 2. So the first advantage is that it decreases the dimension of the integrals. And in fact, you have less master integrals to compute if you want only to compute delta 2. I must say that in the 2-loop computation, we wanted to prove everything. So we also computed all the matching terms. So we had to compute them. But if you want only to compute delta 2, you could only consider the 9 master integrals that I showed in the last part. Also, one advantage is that we wanted to keep a covariant formalism everywhere, especially in the velocity cuts, and not consider velocity expansion, because as I showed, I think there could be problems if you do just a velocity expansion because of the non-commutativity of the epsilon goes to 0 and the sigma goes to 1 limit. What we were able to do also with the method is identify exactly, so separate the potential contribution from the radiation reaction 1, and show how the -1 power epsilon arise very naturally, so that it proves also the relation between the imaginary divergent part of the delta 2 and the finite real part. And also we have seen that the integrals are the same both in inequality and in ancient gravity. And you don't need also extra integrals so if you compute the potential region contribution, you don't need to add integrals to get the radiation reaction terms. You just, in two-loop, you just have to add one constant of integration that you put 0 in the potential region computation, and it's not 0 in the radiation if you do a full soft computation. But I have to say that, so you need no new integral, but you need the new diagrams. So for example, you need the self-energy at two-loop in gravity, in Einstein gravity, to get the full radiation reaction terms. So at the end, we proved that there is a one-to-one correspondence between the classification in terms of the number and the type of velocity cuts you insert, and the terms that appear in the iconal matching. So at higher loop order, we could expect that you will just have to focus on this kind of integrals when you take n at n loop, you take n velocity cuts with L different internal momenta, so that it would contribute to delta m. But I mean, it's just conjecture here, but we hope that it will be helpful to simplify the computation at higher loop orders. So I'm finished here. I think it's 45 minutes, but if you have a question, I would be happy to answer.
Yes. Well, thanks very much, Ludovic, for the great talk. And we already have a hand up from Julio. Please go ahead with your question or comment.
Hi, thanks a lot for a very nice talk. I have two questions actually. So first, this method, how does it work as an algorithm? Like if I hand you an integral, how can you tell the ones that you need to combine it with to localize the delta functions? Do you know, for instance, at 3 loops, what would be the families of integrals, or do you need to look case by case and try?
No, so the way we did it is not, so we didn't take all the integrals at 2 loop and said, oh, okay, well, I have to take the delta function like this or this or this. We just saw in the integram the symmetries and then identify the integrals you need to compute for the 2 loop computation, and that we computed it. But I don't know if at 3 loop, so I think it's, you could make some general rules, but for example, I will just come back to, if you take, for example, G, so G and P, for example, it's not obvious to how to take the delta function if I give you an individual integral, because you have some issue with, so you have to take care of the I epsilon prescription in the massive propagator, and it is really the sum of integrals coming in the amplitude that will generate delta function. And it's not really easy at the integral level to say, okay, I have to take delta function like this or this, and this is what will contribute to the amplitude. But maybe I think there could be some general rules, but I don't know them at 3 loop. And at 2 loop, I think it could be feasible, but at 3 loop, I don't know.
Okay, thanks. And my second question, so about this non-commutativity of limits. So I mean, yes, what you showed us is that certain integral is scaleless in the potential region. But we know that there is another region, which is radiation, which precisely has this velocity to the epsilon dependence, this like this I5 integral that you have on the screen. So you can still compute boundary conditions by expanding in velocity. You just need to include all the regions. So I'm a bit confused why there is talk about commutativity of limits. Like if you add all the regions, then there is no problem with any commutativity of limits. You just get the full result for the integral. So maybe I misunderstood what is the point that you were trying to make.
So in fact, if you look at I5, I think it's obvious that there is a non-commutativity of limits, because if I take sigma equal 1 before epsilon goes to 0, you don't have the same result than epsilon goes to 0 before sigma equal 1. So the non-commutativity of limits in the full soft result for the integral is here. So I mean, so I talk about region, potential region and soft, because I think there are computation that are doing integration by region. But in fact, in the computation, we didn't do a potential region versus radiation. We just do the soft expansion. So this is the only assumption we make, that you expand in Q. And then you have some integrals that are generated, and you compute the integrals. And there is a unique value for the integral, and we compute the integral. And we don't do, if I did the separation here, it's just to compare the potential results and that are in the literature versus the radiation reaction. But there is a one single value for every integral in the soft region, and this is what we computed.
Right. So I agree with that. It's just that the method of regions also works to capture those pieces, and you can expand in velocity. So I agree with everything you said, and the final result, there seems to be a commutativity of limits, but if you add all the regions, as I said, you get this result. So there's no ambiguity. In fact, there's this extra region. So you got these 11/3, which is what sometimes is called the quantum soft region. So that thing is really interference between classical and quantum stuff. And if you expand in velocity, that is set to 0. So there's integrals which are set to 0, and they don't contribute to classical physics. I think in your formalism, probably it only matters when you're manipulating things, because you get to the same basis that the Bornline people use.
Exactly.
But for instance, this bubble box integral, that thing, if you add a potential plus radiation, it's 0. So we can discuss whether that 11/3 has any classical significance, but I think most people believe that only the potential and radiation regions are relevant for classical physics, whereas the full soft.
Sorry, I don't understand what 11/3 you were referring to.
The result for the amplitude you showed, there wasn't.
Yes, but it's classical. I mean, you need this to match. You need all of this to. This is the radiation in gravity.
Sorry. This is just the. I didn't mean the 11/3. So you were talking about the bubble box integral.
Yes.
At some point, yeah, that one. I think you just passed that. Well, you talk about the factorization, yeah. So the bubble box, there's many contributions here, that all of these contributions that are some quantum piece with some classical piece that gives something which looks naively classical. And all of those, they're there in the soft region, but they won't be there if you expand in velocity and you include all different regions.
Okay, but in fact, we didn't do integration by region. We just do a soft expansion and computation of the integral. So
yeah, sure. I'm just commenting that you had to go back to one loop and to compute a quantum correction in order to extract the classical answer. And at high orders, it will get worse, because you have to compute to high order in quantum at the previous loop orders to extract the classical piece. And all of that comes from the difference between potential plus radiation and full soft. So I think it would be very nice if one can find a way to streamline the calculation in potential plus radiation rather than full soft to avoid all of this.
That's what we do.
Yeah, sure. I mean, because you already took the log.
Yes.
But yeah.
What Julio is trying to tell you, Ludovic, is that you can uplift that 0 from the potential in the boundary condition from the radiation, which is how we do the calculation. And there is nothing wrong. You just have to be careful, because there is 1 over beta or 1 over velocity expansion. So the scaling is a little different. And one other thing is that you don't necessarily, your calculation doesn't get the radiation reaction in our approach exactly. There's one more, because now the U direction matters. So there's one more integral that you need to include. So it's not the same that we use for potential. And there is also the issue with the boundary conditions, retarded versus Feynman. At 2 loop, it doesn't matter, but at higher orders, it's this whole issue with the memory and details, etc., that will bite you back. And that's why you need KMOC or something else. But we can discuss about that.
Maybe I can ask a quick follow-up question. So, so when you organize these integrals into delta function, can you say a bit more like how does that rely on the numerator structure? So for example, if I give you the result that's before IBP reduction, is that easy to see how you organize into these delta functions?
Yes, so I think we put that in the, I don't have it in the slides, but you can expand the numerators also in P1 bar and Q dot L, and then you see that you have some symmetry in the integrand, including numerators. So that you can in fact reduce the numerators at the level of this basis after having taken the delta function.
See, but okay, I see. Thank you.
So, are there any other questions or comments?
Maybe I have one. At some point you were talking about the 3 graviton cut. Did I understand correctly?
Yes, yes.
So that got me confused because I thought you were only cutting the massive lines.
No, in fact, so the
This is not a velocity cut, right? It's something.
Yes, this is a unitarity cut. So you do the unitarity cut and you do the product of the 2, 3 amplitudes. And then when you organize the integrand, you see that the velocity cut appears and the delta function appears.
But why do you want to do the unitarity cut?
Because you don't want to compute the gravity integrand with Feynman rules. I mean, it's easier to get the integrand with the unitarity cut.
But this you only do when you go to Einstein.
Yes. For n=8, we take just the general formula for the integrand.
I see. For gravity, it's harder to proceed in the other way.
Exactly.
Mm-hmm. Mm-hmm. And I don't know, just a very general question because I'm not an expert on these things, but I mean, so you start with Feynman propagators all over the place.
Yes.
And then you manipulate your propagators, expanding, I guess, in delta functions and principal parts.
Yes.
And then you have to collect according to the number of delta functions.
Yes. So you see that for the double box, you have some plus I epsilon for this P1, but minus I epsilon for this P1 because you have P1 plus Li square, but here you have P1 prime minus L1, for example.
That's right.
Well, so
but this is always Feynman.
Yes.
It's a Feynman propagator. And then now you, I mean, to get to your velocity cuts, you simply expand. So
you have to expand and organize your
and reorganize. And there is a unique way to bookkeep everything. Huh?
Sorry?
There is a unique way to keep your bookkeeping of terms. Okay.
Yes.
So, and then you say the shortcut would be, in order to compute the classical things at n loops, to keep the terms which have n delta functions?
Yes. Mm-hmm. But it is linked to the first question of Julio also, because if you take an individual integral, it's not for at n loop, it's not easy to say, okay, I have to take this cut with this symmetry factor, for example, because you will have a sum of n, I don't know how many integrals that will contribute and form a delta function. So it's not easy from.
It's not easy.
Yes.
Mm-hmm. Mm-hmm. Because you have some diagrams before doing this. You have put together different terms, different contributions. Is that
yes? Yes.
Okay. Okay.
I think just a comment. So I think the challenge is to bookkeep the h bar over h bars that proliferate at high orders. So I'm confident that this. I mean, they found a way to do it, which is awesome, and this had to exist because the word line calculation exists. But I think what's going to be more challenging compared to the word line calculation is to keep track of all of these quantum times classical and see how they organize in a way that you can ignore ahead of time. So if we need to compute the 4-graviton cut at 3 loops, then probably we're toast, because the 4-graviton cut at 3 loops is it's a real beast. So if one could go directly from cuts with matter propagator cuts to the pieces here, that would be essentially as good as the word line calculation.
I see.
But in fact, so you see that the amplitude has some redundancy of information, because there are a lot of iteration of subloop integrals, subloop contributions. But on the other side, in the word line, I don't know exactly how the double box contribution, for example, emerge, or the self energy. So perhaps the amplitude has too much information, but it has all the information from the beginning. So you just have to classify the information and be able to focus exactly on the information that will contribute to the angle, to the observables.
Yeah, I agree. It's just, the word line directly computes the iconal phase, basically.
Yes.
Whereas you have still to subtract. So, and I just think the subtraction will get harder at higher loops because of this interference between quantum and classical, unless we get smarter and smarter. So you guys already figure out how to do it at 2 loops in a streamlined way. Yeah, so that's very nice.
I mean, can I ask a question just to see if I understand? You talk about the 3-graviton cut, but in practice you take 2 amplitudes, two scalar in 3 graviton, and you solve them together with the propagator. That's what you do, essentially.
Yes.
And then you say that in n equal 8, that's all you have to do.
No, I do that in Einstein gravity. So in n equal 8, you take you have the full expression for the integrand. So you take the full integrand, but in gravity you have to do unitarity cuts to get the integrand for the double box and all the topologies.
But if you take the amplitude like you have there without cutting it, and then you expand the numerator and you cancel the propagator, don't you get all the terms that you have in equation 14?
Yes, you do, but I think you don't want to do all the Feynman graph in gravity.
Not you're not doing Feynman diagram. You are just expanding the numerator, canceling some of the propagator. Or
yes,
not?
But how do you get the numericals for the box triangle if you don't compute the Feynman diagrams? If you don't choose unitarity cuts, I mean.
You're just using generalized unitarity, right? That's what you're saying, that you're using the unitarity method to get the integrand. It's a 2-step procedure. First, you get the integrand from unitarity. Second, you organize it and you integrate.
Exactly.
But I mean, the integrand is without the propagator of the graviton. But in your expression, you have the propagator of the gravitons.
Yes.
So in what sense you cut? The propagator is there. I mean.
Yes, but you cut. I mean, you just do unitarity because I mean there is nothing original in this in what we do.
No, but I mean you don't put a delta function. You put 1/q squared.
No, so it's not a velocity cut here. So you don't put a delta function. It's just
then you shouldn't talk about unitarity cut.
No, it is a unitarity cut, but it's what SME also does. You reinstate the propagator. You don't put the cut. It's the discontinuity.
Yeah, but I mean, if you were in the physical region of the T channel, then it would be a real cut where your 2 particles annihilate into 3 gravitons. That I understand as a unitarity cut.
No, sometimes we call this a generalized unitarity cut to avoid.
Okay, that
Yes.
sounds better.
It's just the residue of the integrand.
Yes, that's right. You compute the residue and then you stick in the pole.
Yeah.
Yes.
Okay.
But I mean, in your paper, there is not a computation of the, you compute the amplitude two scalar in three graviton and you saw them together.
Yeah, that's
Yes.
So that's what you do.
yeah.
Yes.
Okay.
Shell. Yeah.
Okay, so with that clarified, I think it's time to thank Ludovic again.
Thank you.
And